Another relationship that we've observed from the world around us is the time it takes for a distance to fall so far. We know that the relationship between the distance an object falls varies directly with the square of time. That's one of these that we already have here. The second one that I have listed is a power relationship that varies directly with a power. So the distance an object falls varies directly with the square of time. So imagine we're driving across a bridge in Twin Falls and we're looking at some base jumpers jumping on off. And we're kind of getting a sense of what can they do? Do they have time to pull the chute or not? And we measured that the time it takes or the distance that someone falls is 64 feet at a time of 2 seconds. My second set of criteria is I'm curious about what's the distance, or what do I have here? Distance. What's the distance after 4.5 seconds? I want to make sure I get my numbers right so we don't hurt somebody with a bad chute deployment. So how can we tell that? What's that distance that the person will fall after 4.5 seconds? Again, our strategy is recognize the correct variation, use my initial set of equations or my initial set of data to solve for my constant proportionality. So I'll have 64 equals my constant proportionality times my time, in this case, which is squared. Solve that for k. 64 divided by 4 equals k. It looks like my constant proportionality is 16. I can use that now for my second set of criteria. So my distance I've fallen, I don't know, equals my constant, which we discovered was 16, times the square, or times the time squared. So my distance that I've fallen will be 16 times 4.5 squared. Sorry, typing in wrong. Not that you've ever done that. Yields a distance of 324 feet. I can see that this fall is not linear, because after 4 seconds, he just didn't fall 128 feet. Rather, after 4.5 seconds, he's fallen almost 4 times, 5 times as much. So we can see the relationship varies directly by a power.